And so let me just briefly share. Okay. So Christian Kästner is a professor at associate professor at CMU with a variety of interests, as I think will be made clear in this talk, where he is going to be talking about a lot of sort of parameters and issues that ideally need to be considered when we're designing ML sorts of efforts. He received his PhD from Otto von Guericke University in Magdeburg, Germany. And for those of you who are unfamiliar with Otto von Guericke, I recommend Googling him or looking him up in Wikipedia. He was quite a Renaissance person back in the 17th century, did a lot of physics stuff with vacuums and putting two balls together and getting, I think, the best vacuum ever achieved at that time, but also electrostatics. But he was also, I think, a diplomat and mayor of the town. He did all sorts of things. So quite an illustrious person and an illustrious alumni of the university. Christian will be talking to us, as the slide says, about toward a system-wide and interdisciplinary perspective on ML system performance. And welcome, Christian, and thank you.
All right, thanks. So my background is in software engineering, and when I was asked to give a talk at a performance workshop, I was kind of wondering how I can do this. So my interest in general is at different facets of software engineering. I've done some performance work, mostly on highly configurable systems, and I've used some machine learning there, but I'm not going to talk about this. I'm actually interested these days in how do we build systems that include machine learning components in them. So production systems, systems that end users would use, and also how to do this in a broad range of settings. So not just the Googles and Facebooks out there, but the many different companies and startups and government organizations that often struggle they build some models, but then struggle putting this into production. And we really need to think about how to do this with interdisciplinary teams where we have data scientists, software engineers, systems people, operators, and end users, and lawyers, and all kinds of people involved. So I'm not so much interested on how to make TensorFlow faster. So I'm interested in, if you have a product and you want to integrate machine learning, how do you do that, right? How does this change your processes? How does this change your collaborations? How do you think about performance in this context? And not just at the model level, but in general. So here, for example, PowerPoint is a system that has been around for a long time, but as all products, they start introducing machine learning. Here's an example, the slide design idea. If you click that button, it makes a couple of suggestions of how to make your slides look nicer, something that I obviously don't use here, but this is backed by machine learning. But what you see here is that machine learning is kind of a small component in a much larger traditional non-machine learning system. As a different example, one that I use a lot, think about you doing audio transcription and you did kind of speech recognition research. You invested a lot into kind of building the model that can take an audio file and produce text, and you want to turn this into a startup. Doing transcription service, something that we as researchers use a lot. When we interview people, then we have an audio file, and we need to transcribe it to analyze it later. So we upload an audio file. It used to be done by humans and crowdsourced, and now this is almost exclusively done by machines. Artificial intelligence. And again, you have a model here, and that's kind of the key part, right? Without that model, you probably wouldn't have a business, you wouldn't start anything here, but you have lots of things that are around that model. So it's not just the speech recognition. You need to build a system that can actually accept the audio files, transcribe them, show the results, do some payment processing. So you actually have a lot of components in the system. Some are machine learning, some are non-machine learning. And even though the machine learning part here is really the central part of this system, you need to think about the system as a whole. And I have a bit of a frustration in kind of when talking about machine learning, we often focus very closely on the model and we kind of ignore the system in a lot of cases, kind of the larger environment and how it influences each other. So traditional course students would take on machine learning focuses really on the modeling technique. It focuses on the statistics or how to do the feature engineering, how to build a model. And you typically start by being given a data set. you produce a model, you evaluate the accuracy, and then you're happy or you're not, but you're not deploying this. You're not using this in production. You're not thinking about usually how to build a business around this. Right? And there's many more opportunities in this area. And especially if you want to productionize some idea where you have a model, you need to have a much larger scope on things. So let's think about this transcription service again for a second. In machine learning, we kind of know the idea of the flywheel, right? The more data you have, the easier you can build better models. Better models lead to better products, and then you attract more users that produce more data, right? So one idea that you typically have is that you want to create this feedback loop where you can actually learn from your users. So in the transcription service, you might want to learn about what are the mistakes that your model is doing in production? How can we learn from this? And there you need to start thinking just beyond the model, not just, you don't just have a static data set. You want to collect more data. You want to collect targeted data to improve things. And how do you do this? And I think there's lots of really subtle, interesting things that you can do just in terms of interface design and how you design the system around it, how the user interface interacts with the model. So traditionally, when we used to do transcription, we would send an audio file and we get a text file back. And then I use a word processor to go through, listen to this again, and fix a couple of typos. Tshaped here actually has a really nice user interface that synchronizes the audio with the text. So I can click somewhere in the text and it jumps to the right location in the audio. So I can play that part, listen to it, jump back a little bit, listen faster. I can also jump in the audio and see the right location in the text. And in addition, the text here shows me where the model is not quite as certain. So this is something that's actually super convenient, much better than what I used to do in a kind of a text processor listening to this. And it encourages me to stay on the website and change the text here. And by doing this, they can actually observe what are all the corrections that I'm making. It provides very granular feedback about things that are potentially misrecognized, things that can be used later for improving the model, right? Gathering more training data. And all of this happens through kind of a system level design, thinking about how do we collect telemetry? How can the model support us, for example, by providing estimates of where it's unsure? How do I design this such a way that the output actually stores timestamps in a very granular way that I can sync this? Right, so if we think about this again, we have the speech recognition model and it's really important. But if we really want to think about a production system, something that we can deploy, that we can use, that we can profit of, we need to think about the rest of the system too. And they actually influence each other. And technically, we don't really just think about the one model that makes predictions. We also need to think about the pipeline that produces a model, that we can retrain the model, and a lot of kind of monitoring infrastructure. And typically we have multiple models too, and they influence each other in both directions. And so this is really what I want to focus about, that you need to have a system view. Performance is one of them, and I get there in a second, but thinking about how you have different machine learning and non-machine learning parts in the system, and the different qualities actually will help you to design systems better, will help you to think about how to deploy something. So whenever you're designing a system, you have lots of qualities in mind, and there are always lots of trade-offs. In our master's program, we have the running joke that for a software engineer, the answer to every question is it depends, right? So you have multiple design options. Which do you use? It depends. The mark of a good engineer, though, is that they can explain what are the different options and what does it depend on, right? They can make a judgment call and justify why they suggest a specific solution. So in the machine learning systems, there are all these qualities that matter. At the model level, the obvious ones are accuracy, and then all the performance-related things like inference latency, throughput, energy consumption, at the inference time, at the learning time, how long learning takes, whether you can do this incrementally, what kind of resources you have. You have a bunch of other qualities that come up, right? Interpretability, fairness, robustness, and so on. But then you also have all these qualities at the system level. usability, profit that you're making, cost per prediction, usability, user satisfaction, how do you deal with mistakes, safety, security, which are all system level properties, right? You can't do a huge amount at the model only. And actually, the system quality does not necessarily align very well with the model quality. There are lots of interesting examples. One that I pick here is Booking.com. They're in the business of selling you hotel sites, and they do a lot of machine learning. They do a lot of predictions of, are you a business traveler? Are you traveling with your family? Are your dates flexible, to kind of give you different recommendations? And they do a lot of studies, a lot of online experiments where they kind of see what's the accuracy of their models and how is their business doing? And they care about the conversion rate, how many hotels they're selling. And they see in some cases, as expected, if you have more accurate models, you make more sales. But they also have a lot of cases where more accurate models don't actually do that much. So there's kind of a saturation, right? The model is good enough. Beyond that, you don't gain much more benefits. And they actually have negative cases as well, where the model gets much more accurate, but they sell less. And they have a couple of different explanations for this. One that I find very interesting is they talk about an uncanny valley effect, where the predictions get so good that they become creepy. So you get to the website, you don't enter a lot of information, and it starts knowing things about you, and you don't really want to book with them anymore, right? So they're really weird effects sometimes. So you really, in the end, care mostly about system quality more than model quality. And also, good enough might be good enough, right? So when you have all these qualities of interest, there are lots of trade-offs. And just to walk through some of them, let me give you one more example that I use in my class as well. This is a picture in Korea, and I can read almost nothing here. I can recognize the Taco Bell on the side, but that's about it, right? But we have pretty good translation apps. So there's actually this augmented reality thing that Google has been doing for over couple of years now, where you can hold your camera up, and it will, in the live image, the live video that you're seeing, translate things immediately, right? So let's assume we want to build something like this, but build it in a new generation of kind of augmented reality smart glasses, right? So if we're doing this kind of thing, we have lots of design challenges. We probably need multiple models. We need a translation model. We need something that detects characters, some OCR thing in the video stream, probably some image stabilization that if we move our head, that kind of moves with it. And we can deploy this in different ways. We can deploy this on the glasses, which is where the camera and the display are. We can deploy it on a phone that's probably connected to Bluetooth. We can connect it to the cloud. Deploy it, and we can deploy them in some sort of hybrid ways. And whatever we're doing, the different kinds of models that we're doing, where we deploy them, and lots of other decisions, they have all kinds of trade-offs. Right? So typically we know that there are lots of different kind of models. Some are more accurate, some we can get to much smaller model sizes that we can, like deep neural networks are not the most energy efficient. Maybe we can avoid that, at least on the glasses, right? When we run this on the cloud, we might not care too much about this because we can just use a couple more machines to run this, right? Latency becomes an issue, latency of the model, but then also latency of the communication, right? So in different kind of designs, can we actually afford to send the data back to the phone, to the cloud? Can we afford that latency? With augmented reality, there's this thing called cyber sickness. If you need actually very quick response rates or very quick updates faster than what you would use in a video conference. Otherwise, you would notice kind of a lag, something that people feel really uncomfortable. So you have like 20 milliseconds, I think, to update things. So there's certain things that you can't do on the phone. You probably also can't stream all the video to the phone anyway over a Bluetooth connection. So certain things that you need to do on the glasses, but do you need to do the translations there too? Do you need to do OCR on every image of a video there? Or is it sufficient if you do this once in a while and the rest you do with image stabilization, right? Lots of possible designs here, lots of trade-offs, and there are many more, right? So for privacy reasons, maybe you don't want to the data to leave the glasses or to leave the phone. But on the other hand, you want some telemetry data. You want to know how your system is doing in production. But you also don't want to send all the video constantly back because you're just overwhelmed with the amount of telemetry data and it's somewhat useless. Right? So you have, again, the benefits that you get from telemetry, the costs of telemetry, the ability to work offline, the ability to preserve privacy for your users, right? So all these kind of issues you need to design, and a lot of them affect decisions that you make about individual models. A lot of them affect decisions that you make about system requirements, maybe even hardware requirements if you can influence them, right? How do you design the smart glasses, things like this. So I could go on forever. There are lots of them. There's lots of trade-offs on the training sides as well, right? Do you need to care? You need to know how often you're updating things to kind of put training costs in perspective. If I kind of go through the CO2 of a small country for one model, maybe that's okay if I'm just training this model once a year, right? Languages don't change that frequently. Characters in languages don't change that frequently. So I don't need daily updates. I just need occasionally updates when I've found better ways of doing these kind of things. So in the end, all of these things, the answer is always it depends, right? There are all these trade-offs all the time, but we really need to understand them, and we can't do this just bottom up by just looking at the model, right? This is actually where it becomes really important to think like an architect or like an engineer, to have the entire system in mind. So traditionally, kind of process has a bad reputation, especially the waterfall process. But the idea here is to make you think before you implement something, because once you build something, it's very hard to beat certain qualities in it after the fact, right? If you have built a system and now you need to make it twice as fast, 10 times as fast, that's really hard than if you have some influence of this in early stages. And just to briefly show this power here, some of you may remember Twitter in the early days. Around 2010, Twitter would go down all the time because they go over capacity. In 2010, there was a soccer world championship. Every time there was a goal, Twitter would go down very reliably, just too much load. So they built this Ruby on Rails application with a couple of friends and then tried to scale it. And the way that they scaled it was buying more machines, way more machines. They were paying a lot on machine costs and adding more caching. So they started adding caches everywhere in their applications. They started taking shortcuts. They made their code actually really unreadable. It became really hard to maintain and add features because they had so many weird things to increase performance, and they still couldn't get it to run. They're really vocal about this. They talked about this a lot. What they did was really deciding we need to redesign this. We can't do this. This is a design level problem. This is not a code level problem or where one technique can be slightly faster. So they stepped back and started thinking about what are the qualities that we really care about, right? And again, in the machine learning sense, you need to care about the system qualities and break this down. What does this mean in terms of machine learning? But they cared about performance, reliability, maintainability, and modifiability in that sequence also. And they went back and thought about, if we design our system for those qualities and we really want to scale, how can we do this? I don't want to go into the details here. This is one of the classic monolith to microservice stories. They also changed the programming language. They made very fundamental changes to their data model. So for example, they now have roughly sortable IDs, that they don't have a bottleneck in their storage system. So all kinds of decisions, but it was fundamental in designing the system and designing the components of the system to work together and to actually scale very well. So whenever we are approaching a machine learning system, that's not trivial, right? We also need to think about, to some degree, what do we want to achieve here, right? In the production system, what are the qualities? What are the priorities between them? What are constraints from the technologies that we have? Do we actually need to do deep neural networks? Do we need to send data over the network? What latency do we have? You probably need to conduct quite some research, explore alternatives, build some prototypes. But this kind of planning, I think, is really important. And this is where a lot of the transition that we've seen fail happens if people build the model first and then try to transition this and don't think about the system in a disciplined way. And a key point here is that to make this work, you need to think about how to manage this in teams and how to integrate this into a process. So we have typically in these teams, we have data scientists, software engineers, and operators. And again, the bigger companies, Google's, Facebook's, they usually know what they're doing. They have more experience. The smaller companies, less so these days. So startups tend to hire a bunch of data scientists. They build these models, and now what? You have traditional organizations where software engineers and data scientists are really siloed off. So they ask the data scientists to build a model, but then they don't talk much until the model is delivered, and then it's back to the software engineers. Same in government organizations. So we've conducted quite a number of interviews and saw those problems over and over again. And to some degree, these different roles have different specialties, so they focus on different things, and that's not a bad thing, right? It takes a lot of knowledge to understand the data science area. It takes a lot of experience and so on, but there are conflicts because they don't even talk the same language. Things like performance means different things. Parameters mean different things to people if they're not used to it. I see this every semester. So I teach a class on building machine learning systems, and the main project is building a recommendation system for something like Netflix. So I simulate the world so that they actually in a virtual machine need to provide recommendations. I simulate 1 million users that are browsing and watching movies, and I give students, so I ask them for a recommendation whenever the simulated user wants to watch something. And I give students a budget of about 800 milliseconds, which I thought was generous. But then I see semester after semester, students with a data science background build models, collaborative filtering, more sophisticated things. And the first time they try to serve those models, they realize they take 20 seconds, minutes to make a prediction, and then they struggle. They kind of need to go back, redesign the model, introduce some caching or some pre-computation, realize that they don't need to predict all movies necessarily, things like this, to really start thinking more systematically about, given certain constraints, how can they build this? But it's not just blaming, I'm not just trying to blame here data scientists, right? So they have, they know what they're doing. They're really specialized in an area, and software engineers are not better when it comes to data science. There are a bunch of studies out there of how naive, self-taught data scientists are. So when a software engineer builds a model, what you typically see is they try something. They don't spend a lot of time on data exploration, not a lot of time on feature engineering. And if the model isn't accurate enough, they tend to have two answers. One is, let's get more data. Two is, let's try deep learning. Right? No debugging, nothing else. We also have in interviews heard quite a few times that data scientists have produced a model and given it to another team to integrate it into a product. And the model, this was usually in form of a notebook, needed to be integrated now. And the software engineers felt they had to rewrite this entirely because it was nowhere near the quality, especially performance requirements that they needed. And in rewriting things, they often broke a lot of assumptions. They made simpler models, and then kind of the teams drifted apart again. So the typical answer, the ideal answer would be to find people that are good at all of these things, right? They are often called unicorns. You see a lot of these kind of pictures where you want people that are good at all the things, math, statistics, actually building systems and so on. The problem is that these unicorns, while they probably exist, they're rare and they're really expensive to hire. And most people justifiably want to specialize in one area, right? We can't do everything equally well. So the much better approach to go there is build actually teams that talk to each other, where you don't silo them off and where you actually make them understand each other. one way of thinking about this that's broadly talked about is T-shaped people. So these are people that have a deep specialty in one area, but they know enough of other areas to know when they need help, to know when they can talk to other people, and then they share a joint language, right? So what you really want, and I think this is much more an education problem than a research problem, what you really want is to educate people that are specialized in one area to appreciate, oh, there's things beyond the model. Somebody needs to think about performance. Somebody needs to think about telemetry. How can I help them? How can I talk to them, right? Ask them questions. Or the software engineer who wants to integrate a model and has certain constraints knows how to talk to this about, to data scientists about this, or how to include the operations people and actually understand what they're doing. Right? So I think the important part is to get a general understanding of the broader constraints and then people with specialty in individual areas. So I think DevOps has had a pretty positive impact of developers and operators were kind of siloed off, kind of had their own backgrounds and so on. But how to, the movement, kind of the idea of DevOps brought them somewhat together. They gain joint responsibilities, joint toolings, things like containers where developers put in more effort in kind of configuration, but they get benefits by more quicker deployments in production and feedback from telemetry data, right? So there was a kind of joint vocabulary, joint tools. People still have their expertise, but they learn to talk to each other and design tools. We see some of this in the ML ops community, which sees a lot of attention between data scientists and putting things into production. But I see very little right now that actually focuses on the productionization of kind of thinking beyond just the model in the system, kind of bringing developers and data scientists closer together, reasoning about performance trade-offs, things like this. Just very briefly, the end, there are a couple of process models. Data scientists go through different steps. This is kind of well understood. There are different forms of drawing this. And also for software engineers, we have different kind of process models. But we don't typically think much about the integration of these two, right? So if you build a project with a machine learning component, you kind of need to integrate both the machine learning component and the non-machine learning components and the interactions, right? So as a rough kind of approximation here, you might want to, in an ideal world, maybe top down, you would collect some requirements for the system, do some design, figure out some of the architecture and trade-offs, and then identify what are the machine learning and non-machine learning components. And they influence each other, right? So there's like the telemetry requirements for the machine learning components. If they can provide us some accuracy or confidence results, we can provide a better user interface, right? And if we can do this, then they can get more data. So you really want to start thinking about who's responsible for that, for what are potential interfaces here? How can we bring this together? And I think this is somewhat ad hoc in a lot of organizations that we talk to. Admittedly, not everybody will go through a top-down model, right? Not everybody follows a waterfall approach, rightfully so. Most machine learning projects, especially very innovative ones, will spend a lot of time working on the component first before they even think about the machine learning model, before they even think about building a product around it, right? So if you can't do the voice recognition, there's no need to think about the user interface of the transcription service. So you typically follow through different trajectories. Some people start more with machine learning parts, some people with non-machine learning parts. But at some points, you need to iterate back. You need to think about how to integrate them, what to revise, and work together here. And I think we need much more attention on those kind of issues. I think this is a good point to wrap up. So what I wanted to talk about is really encourage people to adopt a whole system perspective, kind of a system engineering perspective, if you want, on using machine learning in production, right? To design for quality and the right qualities up front. Don't try to patch this in later, right? We need to understand what quality we care about, what are the trade-offs, and performance is usually a very important one here. but certainly not the only one. Same as accuracy, right? Accuracy is something that's really overemphasized, I think, in a lot of projects. And there are important trade-offs with performance, with safety, with privacy, and so on. So, and the way to do this, and I think the only way to do this, is to do this with interdisciplinary teams, right? We can create awareness for people, but I think we need to bring people together to do this. So we're still talking to lots of organizations about this. If somebody here is interested to explore this more, talk about your process problems or so on, feel free to reach out, and I'm happy to also talk after this. But that's what I have. Thanks.
Thank you very much. So again, if people have questions, you can unmute and ask or post them in the chat session. To get things started, I posted a couple of things in the chat. I mean, you answered some of them, but one of the things you talked about was people who are T-shaped, I-shaped, and generalists. I'm curious, a couple of things. First of all, what fraction of people fall in each of those categories in major development organizations? And to what degree can the T-shaped models scale? I mean, do you reach a point where if you have, I don't know, 1,000 different domains, even very few people could be even have a general knowledge across 1,000 domains if you get that big? So
right. So first of all, I don't have statistics of which kind of people are most common, but you hear very different things from different organizations. So if you talk to big tech companies, they have been at this for a while, and they kind of cross-train their people, and they kind of brought them together that they have fewer of those communication problems. So they also hire kind of with a high standard, right? And when they hire data scientists, they also go through technical interviews, so they have some experience there as well, right? In smaller organizations, startups, it's often very skewed. So you often start with people in one role that are really specialists in this, and that's why you hire them. And it takes a while to build teams. So a lot of training, I think, can happen on the job, but I think we can do a lot more to prepare people for this. I think when people come out of university, especially with a PhD, they focus very clearly on one narrow thing. Same, that was true for me back then, right? And I think it takes a while to broaden out. And I think we can do something with education there, but certainly not everything. And you're right, there are so many topics out there. And so in my class on kind of teaching machine learning in production, software engineering for AI, I have one single lecture on distributed systems, right? So the goal is not to teach everybody details of distributed systems. They should take a full course on this if they want to understand details, but they should understand the basic concerns, that they can talk to somebody, that they understand what are the constraints here, the trade-offs, right? And talk to somebody, get help and know their language, for example, right? What are the things to ask for?
Thank you.
Christian, I have a question that with these tools like Qflow or AutoML, the boundary between different silos is getting erased, right? Now, like the data scientists can just work with Qflow pipelines, and their models can be like most of the steps will be automated. Even the deployment and the scalability can be taken care of. Then is it true that still we need T-shaped people? Or I'm saying that in this way, with these tools which are helping any non-experts in systems engineering to use machine learning on cloud, for example, how do you see that?
So you see those discussions in both ways, right? So you say people, software 2.0, we don't need programmers anymore. And you see people that say, oh, we get AutoML, so we don't need data scientists anymore, right? And I think we're getting rid of a lot of routine tasks. We're automating a lot of things so that we can focus more on other parts of the pipelines. But I think there are still very specific specialties. I think my suspicion is that we have fewer people who do deep neural network architectures in the future, right? So a lot of this is starting to standardize, and kind of AutoML takes care of some of this, but we still need people who really understand data cleaning, understand the data collection process, right? Understand how to evaluate models in a careful way for biases and things like this. So I think we will still need a lot of people who are really specialists and understand these machines. And we still need architects, software engineers who actually know how to think about the larger system, right? We won't automate all of this away. And I think we will continue. We may see some emphasis on some roles and less on other roles, right? So I hear that, for example, data engineering might become more important than data science at some point, right? But I think the larger story that we need people with different specialties doesn't change that much.
Right. And just to add to it, do you propose that we should develop T-shaped people, or an I-shaped person can be with experience and working on different projects during his job can become like a T-shape, right? Because initially they may be specialists in one, but when they are given opportunities to work on different projects and gather exposure to other things. Yes.
So I don't know what the right position is, whether you do this in hiring. So you hire T-shaped people, or you hire I-shaped people and then train them, right? It probably depends a lot on your organization and the capabilities that you have. I think a lot of this people will pick up on time, but you can really, I'm talking here for our universities probably, right? But with a course, you can probably speed this up by quite a bit and get them much faster into a good team position in a company. We had always this discussions, do we actually need to teach software engineering? Do we need to teach version control and things like this at the university? People are picking this up in companies anyway, right? Of course, we can hire people who are just know the theory, but I think if they have some practical experience and know some of the tools, they can just start quicker, right? And I think are also more competitive in a lot of places.
Thank you.
Okay, so I think in the interest of time, we probably need to move on, but a very interesting, broad set of ideas. Thank you very much, Christian.
Sure, thanks.
So let me stop this recording.